In this video we're going to examine exponential functions, which are functions of the form y equals a to the x. We will begin by looking at the function with base 2, that is the function 2 to the x, then a couple of other bases before looking at a special case called the exponential function, which has special properties under differentiation. Exponential functions are functions of this form: f of x equals a to the power of x, where a is a positive real number. In order to investigate their behaviour, let's look first at the function f of x equals 2 to the x. Here is a table of values for integer values of x running from -5 to 5. If we plot the function y equals f of x, we get a curve that looks like this. There are a few key things to note about the behaviour of this function. We can see that as x increases, y increases. In this case, because the curve is y equals 2 to the x, the value of y doubles each time x increases by 1. This also means that the gradient keeps increasing. This is typical exponential behaviour. We can also see that for negative x, as x decreases, the function tends to 0. However, it always has a positive value, i.e. it never reaches 0. We say the curve is asymptotic to the x-axis, or equivalently, that the x-axis is an asymptote. The last thing to note is that the curve crosses the y-axis at y equals 1, which just follows from the fact that 2 to the power of 0 is 1. Let's look now at the function f of x equals 3 to the power of x. We can see that this function exhibits similar behaviour. The function is always positive, it increases with x with an ever-increasing gradient. The x-axis is an asymptote as x decreases, and it passes through the point 0, 1. Now, what happens in the case where the base is less than 1? Here we see the graph of y equals 0.5 to the power of x. This has similar behaviour again, but the form of the curve is reflected about the y-axis. It's easy to see why if we rewrite the function as 1/2 to the power of x. This can also be written as 1 divided by 2 to the power of x, and we know from the rules of indices that this is equal to 2 to the power of minus x. In this case, the function increases as x decreases, as does the gradient, and the x-axis is an asymptote as x increases. The curve still passes through the point 0, 1 and is always positive. This behaviour is the same for all exponential functions except the case a equals 1, which just has a constant value of 1 since 1 raised to any power is just 1. If a is greater than 1, we get behaviour of the type we saw for 2 to the power of x and 3 to the power of x. And if a is between 0 and 1, we get behaviour like the case a equals 1/2. Let's return now to the first two exponential functions we looked at, 2 to the x and 3 to the x. I'm going to zoom in on the point 0, 1, where the curves intercept the y-axis, and estimate the gradients of these two curves at that point. Looking at 2 to the x first, we can draw a tangent to the curve at 0, 1 to estimate the gradient. We get a value of approximately 0.7. Doing the same thing for y equals 3 to the x, we get an approximate gradient of 1.1. Now, there must be a number which is between 2 and 3 for which the graph of y equals a to the x has a gradient of 1 at 0, 1. This curve will intercept y equals 2 to the x and y equals 3 to the x at 0, 1, and will lie between them everywhere else. We will see that this particular exponential function has special properties which are very useful in calculus. Note that at this point we know nothing about the value of the base a other than it is between 2 and 3. What defines it is the value of the gradient at the y-intercept. From this point I'm going to use the letter e to denote this base, since this is the standard notation for this special exponential. We are now going to zoom in on the y-intercept and examine how the gradient behaves using a more precise tool. Differentiation from first principles. If you aren't familiar with this method, I recommend viewing my video entitled "What is differentiation?" before proceeding further. Okay, so here we see the point where the curve of y equals e to the x intercepts the y-axis. We know that the tangent of the curve at that point has a gradient of 1. Let's label the point 0, 1 as a, and consider a point b on the curve a distance delta x away from a in the x direction. We're going to first find the gradient of the chord AB. The x-coordinate of b is delta x. Thus, it must have y-coordinate e to the delta x, since b lies on the curve y equals e to the x. In other words, b has coordinates delta x, e to the delta x. This means that the increase in y between a and b is e to the delta x minus 1. Thus, the gradient of the line AB is e to the delta x minus 1 over delta x. Now, differentiation from first principles tells us that the gradient at a is given by the value of the gradient of AB as delta x tends to 0. And we know that the gradient at a is 1. Thus, we can write the limit as delta x tends to 0 of e to the delta x minus 1 divided by delta x equals 1. Now let's consider 2 points on the curve a and b away from the intercept. Let's suppose that a is the point x e to the x, and that b is again a distance delta x away from a in the x direction. As before, we're going to find the gradient of AB. Well, the point B must have coordinates x plus delta x, e to the x plus delta x, since its x-coordinate is x plus delta x and it lies on the curve y equals e to the x. Thus, the increase in y between a and b is e to the x plus delta x minus e to the x, and the gradient of AB is e to the x plus delta x minus e to the x over delta x. Looking at the numerator, there's a common factor of e to the x, which we can take out of the expression for the gradient, expressing it as shown here. Finally, to find the gradient at a, we find the limit of this expression as delta x tends to 0. The factor e to the x is not dependent on delta x, and thus this can be taken outside of the limit. Now we have something really interesting, as if we compare this limit to the expression we derived earlier, we can see that this limit equals 1, meaning that dy by dx is simply e to the x. This unique function thus has the special property that the gradient at any point has the same value as the function itself. Or, to put it another way, the function is unchanged under differentiation. This makes it a very important function in calculus, enabling us to solve all sorts of problems we would not otherwise be able to. Up to this point we have said nothing about the value of e, other than it is between 2 and 3. E is in fact an irrational number like pi. It has an infinite number of non-repeating decimal places. Thus we can't calculate it exactly, but can calculate it to any level of accuracy. How we do that is not dealt with here. To 5 decimal places, e has the value 2.71828. Because of the special properties of e to the x, i.e. the exponential function that has base e, the logarithm to base e also has special properties. We define the natural logarithm to be the logarithm to base e, and we usually denote this by ln, which is pronounced simply as ln. We know from the definition of logarithms that ln e to the x equals e to the ln x equals x. And we also know that the natural logarithm function is the inverse of the exponential function. As with any inverse, to plot ln x we simply switch the x and y axes from the exponential function, resulting in the graph shown here. Notice that although the gradient is always decreasing as x increases, the gradient of the natural logarithm function never becomes 0, and the function can take values that are arbitrarily large. This is obvious when we think about the corresponding values on the graph of y equals e to the x. There are no values of x for which e to the x doesn't exist. It just gets very big. Finally, we want to know how to differentiate the natural logarithm. If we write y equals ln x, then we know, by definition, that x equals e to the y. Well, we know how to differentiate this. We have dx by dy equals e to the y. Now we can apply a standard result from calculus that dy by dx equals 1 over dx by dy. This result is straightforward to prove from first principles, but I'm not going to do that here. This means that dy by dx equals 1 over e to the y, and we know that x equals e to the y. Thus, dy by dx equals 1 over x. This is also an important result, which is especially useful when it comes to integration. But that is the subject for another video.